Good afternoon everyone, and welcome to today's worked exam answer video. Today I'm having a look at a required practical based question. These are so important, and I don't think that the required practicals in regards to how they will be examined and what you need to know in terms of those required practical for the exams is often covered in sufficient detail for students to really understand what they need to be able to do. Now, this particular type of question is something that AQA are using more and more, which is to give you part of a method and then ask you either to spot the mistakes or, in this case, suggest improvements to the method. So that's what we're going to be doing here, and we're going to be doing that for the preparation of a standard solution of sodium carbonate, which is a part of required practical 1, which is to make a standard solution and then use that standard solution in a titration. The second part of this question is then thinking about percentage uncertainty, and again, this is something in my experience that is often not very well understood. So I thought this was the perfect question to start off the week. And because it's required practical 1, this is relevant to all year 12 students as well as all of those of you in year 13. Now, you might get a prepare a standard solution question, which is a 6-marker where you have to outline the whole method. And in some respects, that's harder because you've got to remember the whole method, but in some respects it's slightly easier because once you've learned all of the steps of preparing a standard solution, you're just regurgitating that in a nice, concise manner to get all of the marks on a question like that. It can be much more difficult to try and spot mistakes in something that has already been half written for you, which is exactly what has happened here. So the method steps that we've been given are as follows. So we're going to weigh a clean, dry, empty container on a balance that reads to 2 decimal places. We're going to add about 2.5 grams of solid sodium carbonate to the container. Then we're going to tip that solid into a beaker. We're then going to add approximately 100 centimetres cubed of distilled water to the beaker. We're going to stir until all of the solid has dissolved. We would then pour the solution into a 250 centimetre cubed volumetric flask, and then we're going to add distilled water until the top of the meniscus is level with the graduation mark on the volumetric flask. Now, if we just read that, there's nothing there that sounds horrific, that's very obviously wrong. But we still have to suggest 3 improvements. Whoops. That can be really hard to do, like I say. In terms of the 3 that jumped out at me immediately, so perhaps not the more obvious ones necessarily, but steps that are completely missing. First of all, we've added approximately 2.5 grams of solid into the container and then tipped that into our beaker. But how do we know exactly what mass of sodium carbonate is in the beaker? Because the idea of a standard solution is that a standard solution has a known concentration, and that's because we know exactly the mass of whatever substance it is that's gone into the volumetric flask, and we have very carefully and accurately added a known 250 centimetre volume to that solid in that volumetric flask. So if we don't know the exact mass of solid we've added, we're not going to be able to know a specific concentration. And then if we then use the standard solution in a titration, then we're going to get very inaccurate results because we don't actually know what concentration of sodium carbonate solution we're using. So the first improvement, and we should always be doing this anytime we're weighing out a solid and then we're tipping it into a beaker or anything else, we always have to reweigh the container or reweigh the weighing boat so that we know the exact mass of solid transferred, and that is known as weighing by difference. So we weigh it when the container's full, we then empty it, and then we weigh it again, and it's the difference between the mass when it was full and then the mass at the end once you've tipped out what you believe is all of the solid. That tells you the mass that you've actually transferred. So improvement number 1 is to reweigh the container slash, you can use the phrase weigh by difference, to deduce the actual mass of sodium carbonate transferred to the beaker. Okay, the next step that's completely missing is to do with the dissolving of the solid sodium carbonate into the 100 centimetres cubed of distilled water, and then we pour that into the volumetric flask. Now, in just the same way that we might leave some solid behind in the container, we might leave some dregs of solution in the beaker. And if we've stirred the solid in the solution with a stirring rod, there is a chance that there will be some solution on there. And if there's solution on there, that means there's going to be moles of, well, parts of the mass obviously, but there'll be moles that are not in the actual volumetric flask. So we should always be rinsing the beaker and rinsing the stirring rod with distilled water, and then transferring those washings, is what we call them, into the volumetric flask as well, because that's going to ensure that all of the mass that we've then accounted for by weighing by difference, we then know with a much greater certainty that all of that mass is actually in the volumetric flask, rather than going, oh, well, I know specifically I added 2.25 grams of solid sodium carbonate into the beaker. There's no good you then leaving 0.25 grams of that behind. We need to ensure everything gets into the volumetric flask. So I would say rinse the beaker and stirring rod with distilled water, which is what they're using in the question, so I'm following suit, with distilled water, and transfer the rinsings into the volumetric flask. And then the third step that is omitted completely is the final step. So once we've added the distilled water to the top of the meniscus, well, until the top, sorry, yeah, the top of the meniscus is level with the graduation mark, because we've got all of the solid that was dissolved in the distilled water in the bottom 100 centimetres cubed of our flask, and we've then added 150 centimetres cubed of just water on the top, if we then were just to take that volumetric flask and then take out of that 250 centimetre cube volumetric flask 25 centimetres cubed to then use in a titration, that's going to come from the top part, which is going to be predominantly water. There will be some mixing naturally, but it's going to be a very different concentration of solution at the top to what it is at the bottom. We have to make sure that the concentration of the solution is the same throughout. So the best way of doing that is put your lid on your volumetric flask and then invert it a number of times so that you get a homogeneous concentration throughout your solution. So the final step, which would be step, well, 7, but it wouldn't be because we'd have to have these steps in as well. So step 9 would be invert the volumetric flask several times. And those, for me, like I say, were not necessarily the 3 obvious ones, but they're the 3 steps that you would have to include if you were thinking about a 6-mark answer and you were just asked to right for 6 marks the method for preparing a standard solution, those 3 things would have to be in there. And obviously they're not in this answer that they have provided us with. The others that you could have mentioned, measuring and recording all the masses to 2 decimal places. If you're using a 2DP balance and it says add about 2.5 grams, well, again, we still need to know what about 2.5 grams we've added. So yeah, recording everything to 2DP. We could have also had, with regards to filling up the volumetric flask, adding the distilled water as we get closer to the meniscus with a pipette. So we can be more careful and we can be therefore more precise with stopping at the point in which the top of the meniscus is on the graduation mark. I think that's probably about it, but like I say, those are the 3 that you would have to talk about if you were to write that method out in full. So those would be the ones that I would be going for. Okay. In the second part, and we can get percentage uncertainty calculations with all sorts of different pieces of apparatus for different types of measurements. So here we're having a look at the percentage uncertainty in the volume of the sodium carbonate solution, which means that we are trying to figure out to what extent 250 centimetres cubed is accurate for the volume that we have prepared. Now, the uncertainty on each piece of equipment is different. You have pieces of equipment that are more precise than others and thus better than others. The smaller the error on the piece of apparatus, the better, because that means that the actual value we've measured is more likely to be true, whereas if there's a bigger error, there's a much bigger range over which that value might be. And those uncertainties on each piece of apparatus, they're nothing that us as humans can control. It's in sort of the production of the apparatus itself, and you will always be given those uncertainties. So here we're told that the uncertainty for the volumetric flask is plus or minus 0.2 centimetres cubed. So that means that if we think we've got 250 centimetres cubed, we might actually have 250.20 centimetres cubed, or we might have 249.80 centimetres cubed. So that's not a massive amount. What we then need to do is convert that into a percentage of the overall volume, in this case, that we have in the flask. So 0.2 as a percentage of the 250 that we measured. So to write that as a little equation, percentage uncertainty is the absolute error on the equipment, and then you would divide that by the measured value. So this could be done with thermometers to measure temperature, it could be done with balances, it could be done with pipettes, burettes, in titrations, any piece of equipment. So we can do it with volumes, we can do it with masses, we can do it with temperatures. They're probably the more common ones that you'll be doing it with. And then we would be timesing that by 100 to turn it into a percentage. So in this question, the absolute error on the piece of apparatus is 0.20, and the measured value is 250 centimetres cubed, and then I would need to times that by 100, and that gives me an incredibly small percentage. So 0.2 divided by 250 gives me 8 times 10 to the minus 4, times that by 100, and I get 0.08%. And the smaller the percentage uncertainty, it's with greater certainty that we can then say that, well, the likelihood is we have 250 centimetres cubed, or very, very close to 250 centimetres cubed. If your apparatus is less precise, the error will be bigger, and thus the percentage uncertainty will be bigger. Now, if we think about the volume that we measured, 250 centimetres cubed is quite a lot, which has also helped to bring down the percentage error. If we were only measuring 20 centimetres cubed as a random comparative volume, if we measured 20 centimetres cubed, there'd be a 1% error, which is a big difference. So the bigger the volume that you're measuring, or the bigger the temperature change that you might be measuring, or the bigger the mass change that you're measuring, again, the smaller the percentage uncertainty. And that's better for saying that our answers are more accurate. So if anyone has any required practical 1 questions or any percentage uncertainty questions, because they can get a little bit trickier than that when we're dealing with those changes in temperature or changes in mass, if anybody wants to send me them to have a look at and do a video on, please, as always, just let me know. Drop me a message, leave a comment on the video, or you can send me an email to missg.tutoringandresources@outlook.com. Thanks so much for watching, guys. I hope you have a really lovely day and smash the week ahead.